There we go. Okay, we are recording. So all right. So first, I just want to say again for the recording, the answer to a couple of questions that were just asked. Um, there's going to be 5 numbered problems on the test, so it's going to be relatively short. One of the problems is going to have multiple parts, which are just kind of lumped together. The test is going to cover 3.1, 3.2, and 3.3, and 4.1, and a little bit of 4.3. 4.2 is not on the test. When I say a little bit of 4.3, I mean the definition of prime numbers and the definition of greatest common divisor. So, and then determining whether or not a number is prime, and determining whether or not a number, like determining what the greatest common divisor between two numbers is, that sort of thing. Oh, and the definition of relatively prime, which means that the BCD is 1. So, so those are just a couple of questions that I answered before we started recording. Now, what were we just talking about before? Tenzin or Samten, you had just asked something.
Yeah, I would like to go over 3.3 a little.
Yes, right. And we were talking about we're going over 3.3 and
it was the big, how to use the big O for time complexity.
Oh, that's right. Yeah, that.
Yeah.
Okay, so I will say we can get into like details and like go over examples soon, but I just want to say that the focus, I decided to narrow the focus for 3.3 into, first of all, just time complexity, not space complexity, and also just analyzing worst case scenario, analyzing worst case time complexity. So, you know, that's like, what's the maximum amount of steps that could be evaluated to solve the problem. So and then you know, we measure worst case in terms of that. Big O, I was having a conversation with Andrew just yesterday about this, and he was explaining to me that because big O is like a upper bound, when you say that a function or like an algorithm is big O of n, for example, that means that it's worst case scenario, the amount of time it takes or the number of steps it takes is going to be less than a linear function of n. So use of big O makes sense when you're talking about analyzing worst case time complexity, since what you're really saying is, well, it's less than this. Like, this is an upper bound for how long it's going to take, right? And then that's the worst case, right? So it could be better than that. It could be lower than that, but that is encompassed in saying it's big O of this. So if it's big O of n squared, then you're saying worst case scenario, it's gonna be an n squared time algorithm. So big omega, on the other hand, big omega is where it's like you flip that inequality around and you're talking about the bottom. So big omega is sometimes used to like measure the best case time scenario, because you're saying, okay, the lower bound for this function, it's going to take at least this much time to complete. So if you want to know like a best case measurement, we talk about big omega. And then big theta is kind of like taking into consideration the lower bound and the upper bound and saying, all right, no matter whether it's best case or worst case, it's going to be within this like band, within this range of times. And when you say that an algorithm is big theta of n squared, for example, that would mean that no matter whether you're talking best case or worst case scenario, it's going to be quadratic time. So that is what we're talking about with algorithms, and using the big O, the big omega, and the big theta is not exactly aligned with the mathematical definition of those terms, because remember that big O, big omega, and big theta were not defined by computer scientists for computer science. They were defined by mathematicians for math. And like, there's other applications. There's applications in like a field called analysis, where if anybody's in Calc 2, you know, Taylor polynomials, you can use Taylor, you can like chop off a Taylor series and analyze, you can chop off a Taylor series and use that to approximate a function. And the big O notation was developed and by people doing mathematical analysis, doing stuff like that, using Taylor polynomials to approximate things, and they use it to like sort of measure the accuracy or the precision of a Taylor polynomial approximation. So anyway, what I mean is just that like the computer science application of those terms is kind of like in the spirit of those terms, right? It's like the sort of idea of an upper bound, a lower bound, and then sort of like an accurate measurement. That's really what we're getting at with the big O, big omega, and big theta. So sorry, that was not what you guys necessarily were asking about, but I thought that was kind of interesting. I wanted to share it with you. I think it kind of like puts it in perspective a bit.
Yeah. That is somewhat interesting. Yeah. I was just wondering if we could go through like a problem, not necessarily on the homework, because there's plenty of them in there, I think. But
let's do a 3.2 example to talk about big O, and then let's do a
3.3 maybe
3.3 to see how we are applying it to the algorithms.
Yeah, because they're definitely related in a way that I saw.
Oh yeah, for sure. I mean, very much. Yeah. Hang on a second. All right, there we go. So let's look at two functions. Let's look at, I'm going to stick with polynomials because most of what we're doing with 3.2 is with polynomials. So let's look at the function f of x is equal to like 2x to the power 5 plus 3x cubed minus x. No, not minus x. Just plus x. I don't want to do too much. Yeah, there we go. Let's just do that one. And then let's compare that to x to the power 5. So first of all, is f of x big O of g of x? Yes or no? And is g of x big O of f of x? Yes or no? And then, yeah, and then we're going to prove maybe just one of these two. What I'm going to ask you on the test is something like this. I'm going to give you two functions and ask you, is this one big O of this other one? If yes, prove it. If no, prove it. Basically. Like a prove or disprove kind of problem like you saw back in chapter 1. So let's just look at the first one. Is f of x big O of g of x?
Yes.
I would say yes.
Sure it is. Definitely. Because they're both degree 5, right? And that's really what matters, isn't it? So let's prove that. There's a lot of different ways you can do this. Well, there's two main approaches that I've seen to doing this. One of them is to basically use this idea that if you compare power functions, they get bigger after k equals 1. Like you can use k equals 1. So, if you look at the power functions, x squared, x cubed, x to the 4th, they all cross each other at 1 right here, right? And between 0 and 1, they're in backwards order. But then after 1, then they're in order from lowest degree to highest degree, right? So you can use that idea to say that, like, for example, if x is greater than 1, then, for example, x is guaranteed to be less than or equal to, or rather, not even less than equal, but actually strictly less than x to the 5th. X cubed is going to be less than x to the 5th as well. So because their degrees are lower, then you can say, so, not then, because the then from the if is more so, already been stated there. So 2x to the 5th plus 3x cubed plus x is going to be less than 2x to the fifth plus 3x to the fifth plus x to the fifth, for x greater than 1, right? And so what I just did there is I replaced these power functions all by x to the fifth, and then that, if you add them up, is 3, 4, 5, 6. It's a 6x to the fifth. So what we can use as our witnesses here are c equals 6 and k equals 1. So that's one approach to doing this. It works very nicely, and it's a very easy way to kind of show that a polynomial is big O of a power function. It works really well for comparing to a power function. If you're comparing two polynomials to each other that have multiple terms and coefficients other than 1, then this approach doesn't work quite as well. But I think this approach is pretty good. The other way I've seen to do it, which the textbook tends to do, is to like, instead of doing it this way, you kind of say 2x to the fifth plus 3x cubed plus x is going to be less than 2x to the fifth plus x to the fifth plus x to the fifth. And so like in this entire term and this entire term get replaced by x to the fifth. But then you have to identify when, for what x value is that going to be valid to adjust what your k equals. And in this case, really, this comparison is valid for x greater than 1, but this comparison here that says x to the fifth is going to be greater than 3x cubed. Really, you're saying 3x cubed is less than x squared x cubed, which is only true, only valid for, I think, x greater than the square root of 3, right? Because the 3 got replaced with an x squared. And so then this, your k is going to have to equal like 2 or something. K could equal 2, and c is going to end up equaling 4. So that's kind of another approach. You have a lower c value, but you're like pushing k outward. You're pushing, pushing k out further, like making k larger so that to accommodate that, basically. Does that help with 3.2?
Where did k equals 2 come from?
It's just the first integer I could think of that's bigger than the square root of 3.
Okay, all right.
K doesn't have to be an integer. It can be a real number. We could have picked k equals the square root of 3, actually. That would have been fine. But I just remember that witnesses don't have to be precise. It's not like there's a specific number you're looking for. It's just like you're just trying to find a number that works. So I just grabbed 2 because it's like bigger than the square root of 3. Fine. Yeah, so we can also prove in this case that g of x is big O of f of x. That is true. That is a little bit, is that a little bit easier or a little bit harder? Let's see. Comparable. This is also true. Yeah, because it turns out these are big O of each other. They're of the same order. They're big theta of each other as well. So yeah, so here we go. So for this one, I think you can just say like yeah, that's just that. Because here you're doubling it, which makes it bigger, and here you're doubling it, which makes it always bigger, and here you're just adding on extra terms, which also is going to make it bigger. So this is true. So basically, your c equals 1, and your k equals 0, or whatever you want. K has to be c has to be a positive number. I think it doesn't matter what real number you pick for k. In this case, they're always bigger as long as. Yeah, at least for positive numbers, it's always bigger. Not for negative numbers, I guess.
if you're like the log function that we compared big O to in the assessment, did you put x greater than 0 or x greater than 1? I can't remember.
Let's address that log question in just a second. First, a question about this problem. For Mahmoud, we were talking about where did the c equals 1 and the k equals 0 come from? So this essentially is saying g of x is less than f of x. And this is for like all x that are positive. Because when multiplying by 2, that is going to give you a bigger number as long as you're multiplying a positive number by a bigger number, right? By 2. Like if you multiply a negative number by 2, it gets smaller. If you multiply a positive number by 2, it gets bigger. So as long as we're talking about positive numbers, g of x is always less than f of x. And so less than 1 times f of x, you know, like we didn't even have to do a multiple of f of x to make it bigger. It's just 1. So like, remember, this is sort of measuring this like growth, but it's proportional. And so this is constant of proportionality that you're kind of looking for in your comparison. That's the c value. In this case, that constant is just 1. You don't even need to double it or anything. Yeah. Let's talk about the log thing. I'm not sure exactly I understood your question, but I do want to say about log that chapter 5, when you get to that with Megan, you're going to prove using something called mathematical induction that for all integers n, positive integers that is, n is strictly less than 2 to the n. And so what that means is that like x is big O of 2 to the x. That you're going to prove that later. And that's established in the section in section 3.2, like in one of the examples, example 7. That's why I gave you a hint about that. So you can essentially like write a proof based on that fact that says like if I take x and say that's less than 2 to the x, you know, for all. Well, if there's a c here, there could be a c here. There's not a c here. Actually, c equals 1. And this is for all x greater than 1. You can just multiply both sides of this by x, and that inequality will still hold because you're only talking about positive numbers, so you don't have to like flip the comparison around. It stays the same. Oh, I'm sorry. I just realized this is not the question you were asking me about. X is big O of 2 to the x, that's true. But from this, you can do a log of both sides and get that log of x is big O of x. And then that's the one we were talking about, multiplying both sides of x, both sides by x. You can multiply both sides of this by x and obtain the x log x is big O of x squared. Does that answer the question you were asking about log?
Yeah, it does.
Okay. Should we move on to 3.3, folks?
I had a question.
Go ahead.
So in the previous example, where g of x was big O, f of x, would we still be correct if we said that k was, instead of equaling 0, was like 1 or anything bigger than 0? Would that still be okay to say?
Yeah.
Yeah.
Yeah, it would, because again, the witnesses aren't precise. There's a lot of wiggle room about all you need is the existence of some numbers that work.
Okay, sounds good. Thank you.
Yeah. Am I still sharing my screen? Can you see my the textbook right now, or are you?
Yes.
Yeah.
Okay, good. Yeah, here, good. We'll see. Yeah, I got it. Okay. So I was thinking we could go into 3.3 and pick a problem to go over as an example. of analyzing complexity. Let's get to the end of the section here. So this is an older edition of the book, but I think the problem numbers or the problems are pretty much the same. There's some variation, some numbers that are different, or some problems that are either removed or added in. But yeah, so let's go over one of these. Any requests?
Maybe the one from the assessment.
Yeah, sure. The number 14, Horner. The Horner algorithm.
Yeah, that one or number 4.
Oh, actually, let's go
Those
with
are the
4.
two.
4 is I think I like 4. 4 is cool. Horner is a little bit more boring. 3 or 4. Let's pick 3 and 4 and maybe go over both of those. That'd be a good comparison, because those two are pretty different from each other. Horner is kind of boring because it's just 2 times n. But I have been grading that, and I'm seeing people pretty much getting that right so far. So yeah, so let's try these two though. So starting with 3, we want to give a big O estimate for the number of operations. For an operation is a comparison or a multiplication. So we're just going to count comparisons used in this segment of an algorithm, ignoring comparisons used to test conditions for loops. So we're not going to worry about the testing, for when we arrive at n. We're not going to worry about that. We just want to worry about we just want to worry about what's going on in here. So let's see. What we're doing here is I is going from 1 to n, j is going from 1 to n, I plus 1 to n, and then m is going to be the maximum of 2 things. So there's going to be a multiplication right here that we have to count. AI times aj is being multiplied together. And then right here is a comparison. We're comparing to see which of those is the biggest, right? Maximum. That's a comparison. So right in this step right here, there are 2 operations. You got a multiplying and a comparison. So that's all we're counting. We're not counting assignments, and we're not counting the additions used to increment the variables or anything like that. We're not counting the comparisons for ending the loops. All right, so then the big real, like, the tough part of this comes in figuring out how many times are we going through the loops. Like, how many times are we actually going to evaluate this line of code right here? Well, it's going to happen once for every time through this for loop. And the number of times that it goes through this for loop is changing. It changes based on what I equals. So like as I goes up, j, the number of different j possibilities is like going down, right? But I is going from 1 to n. So for each value of I, we're going to increment all the way through the j's. So I like to represent this as sort of like a 2-dimensional graph. Like let's put I on the columns here, 1, 2, 3, ... all the way up to n. And then for each column, we're going to have a bunch of different possible j values. Okay, so the j values are going to be like, well, for when I equals 1, okay, so when I equals 1, j is going to start at 1 plus 1, which is going to be 2, and then it's going to go up until it gets to n, right? So then when I equals 2, if you increment I and it goes up to 2, then the first j value is going to be 2 plus 1 is 3. And that's going to go up to n. Now, if I equals 3, 3 plus 1 is 4. So the first j value is going to be 4, and that's going to go up to n. And then that's going to increase until you get to n. And when I equals n, j goes n plus 1 to n, which actually doesn't make any sense. I feel like that's a bug in the code. Like somebody made a mistake. When I is n minus 1, you get to n, right? Because j starts at n minus 1 plus 1, which is n, and stops at n. So it's just n to n is just one option. And then when I gets to n,
Oh yeah, that breaks.
it breaks, doesn't it? What do you mean? So break as in like it's as in like error or something, right?
Yeah, that.
Let's fix this person's code for them. There we go. that'll fix it, right? You think that's okay?
Yeah, that's because then j will go all the way to n.
Yeah, we'll stop I before we go off, before J gets all confused about what it's supposed to be doing. Maybe the way the for loop works, it might not actually break the function. Like it might not actually be a problem. It might just like not evaluate anything because it'll identify the fact that J is already bigger than n, and then just like say never mind, and it might not actually cause an error. But whatever. It's more elegant if we fix it like this so that it makes sense. So yeah, so before we move on, just real quick, what does that max mean? It basically means take the two numbers that we're trying to find the maximum of and compare them. You can do this with an if-else statement. You can say, if AI times AJ is greater than M, then we're going to redefine our M to be equal to that bigger number. Else, don't do anything. Like else, just M equals M. Does that make sense? So that whole max function, it's just a comparison, yeah, and it's a combination of a comparison and else. It's a comparison. If it's bigger, you take that one. If it's smaller or it's not bigger, take the other one. And then whichever one is bigger, assign it to the value of M. So that's what this part is doing. So yeah, so as far as we're concerned about counting, it's just two operations because it's a multiplication and one single comparison. And that's it. So what we see here is adding up all of these. We basically have to do that. And the number of these can be counted with that. This is basically the sum from how many do we have here? We've got 1, and then it'd be 2, 3, 4, 5, and then this is going to be from 2 to n is n minus 1, right? That's how many steps we're going to do. So n minus 2, n minus 3. We basically have to sum these up. N minus 1 plus n minus 2 plus ... all the way plus 1. So there's a formula for this. The formula that you may remember from calculus, which is like 1 plus 2 plus ... plus n. So adding up the first n numbers is n times n plus 1 all over 2. This is the formula you used in like when you first started doing integration calculus. That look familiar?
Yeah.
So you can use this formula here, but this only goes up to n minus 1. So it's like n minus 1 times n minus 1 plus 1 all over 2. So this is replacing the n with the n minus 1. And that's what this ends up being, is just n minus 1 times n over 2. So that's like n squared minus n over 2. Yeah, so that's maybe a little more work than we really needed to do. But I wanted to show you how to calculate the actual time complexity. This is the actual number of operations that are happening, and then take that and multiply it by 2. Actually multiply it by 2 for each time. So the total is actually going to be, yeah, I guess it's actually going to end up being just n squared minus n. But what is that big O of? I mean, normally you just say the polynomial, like as a power function, it's big O of n squared, right? So that's how I would answer this. The actual function is that, the actual number of times, number of operations is n squared minus n. But as a big O estimate, I would take the n squared there. So
Where
this
did n
formula-
squared minus n come from and all? Just
It comes from this, using this formula, replacing n with n minus 1. Yeah, it comes from that because you're just adding up all the number of times that you'd go through the loop. These are the values of j, right? So adding all these up, like how many, or not adding up these numbers, but adding up how many there are. There's n minus 1 of them in the first row and n minus 2 in the second row, and so on until you get down to 1 in the last row. So you're counting how many loops, how many times you're going to go through the loop. In general, if you have nested for loops, like if you have 2 nested for loops, you're pretty much always going to end up with n squared, unless it's like different number of times, in which case it might be like n times m. If you have two, if your input is like 2 different lists of 2 different sizes.
yeah, if it was the case like that, it wouldn't be just n squared, it'd be like n times m, or
Yeah, it'd be like n times m. And basically then you're talking about, well, the function that tells us how many operations are going to happen, the time complexity function, right? Like how, worst case, how many operations. It's a function of 2 variables because your input has 2 different things that are different sizes.
right? So would the time complexity of that be n times n times m or something like that?
Yeah, it would. Yeah, you can have it depend on more than one thing.
That's only if they're nested, right? If they're
Right.
if they're for loops in the same line, would it be like you would add them because they wouldn't happen at the same time?
Yes, that's a good point. Yeah, if they're nested, you multiply them. If you do a for loop through one set and then you finish that loop and then you do a for loop through the other set, that's just adding. Yeah, n plus m. Yeah, good question. So let's compare this with the other one here, right? What did you folks get for this one, by the way? Because you did this on your assignment.
I think it was just n. Oh, big O of n, I think.
Big O event. Oh shoot, no, I screwed that up. Make everything smaller. Anyone else get anything different than n? It's not actually n. It is different from that.
Is it log n?
Yeah, this one is log n. So you wanna say why, Abdul?
So you have that while loop, so while I is less than or equal to n, t is adding I, so that's +1, like operations, and then I is equal to 2 times I, and I is incrementing by 2 times. That's 2, 4, 6, 8, and then that's within the while loop. So 2 raised to L is equal to n. You solve for n, and then you get the log n.
Yeah. Where what is your L representing when you said 2 raised to the L?
Number of loops.
Sweet. Number of loops, yeah. Excellent. So yeah, it has to do with the fact that this I, the index, is doubling every time, but it continues until it exceeds the value of n. So like Abdul was saying, it goes, if I starts at 1, then it's going to be 2, and then it's going to be 4, and then it's going to be 8, and then it's going to be 16. So the question is actually like when when is 2 to the L going to be greater than n? This is what will cause the while loop to end. And so what we want to find is the, like, as soon as that happens, what's the smallest value of L for the smallest, like, when is the first time through the loop that this, that 2 to the L is going to exceed n, and that is when it stops. So we're looking for the smallest n that makes 2 to the L, sorry, the smallest L that makes 2 to the L bigger than n. So what you'd want there is L to be, you actually end up having, I think, the ceiling of log base 2 to the n, because that's when it breaks over. So you want to round up, but it doesn't really matter. For some of you, I gave feedback on whether it was ceiling or floor as I've been grading ceiling or floor. It doesn't really matter in terms of the big O estimate. It's going to be a big O of log n either way. But I do believe it should be a ceiling.
So where did that 2 to the L come from then?
Yeah, it comes from this. It comes from this idea down here, that the value of I is doubling, right? So so what you want to do, it comes from that along with this, right? You want to look at which power of 2 is going to get bigger than n. Oh, I just realized something. Actually, oh, no, I didn't just, no, I did realize something, but it doesn't matter. This is 2 to the 0, this is 2 to the 1, right? This is 2 to the 2, and so on. So actually, at the end of the, if L is the number of loops that happen, at the end of L loops, the value is going to be 2 to the power L. And that's what the while loop checks, is the new value after that loop. And it stops, it terminates after the power of 2 exceeds n. So that's not going to happen n times, right? Like normally, like a lot of times when you're doing a while loop, or like when you're doing a for loop, the index value is increasing by 1, by adding 1. And so then the number of times through the loop, if you go from 1 to n, is n times. But that's not what we're doing here. We're not increasing it by 1, we're doubling it. And that's why it ends up being log instead of linear.
Honestly, I mean, like, not that I don't understand log that much, but I'm so used to using it in a mathematical context that when it comes to, like, specifically with numbers, when it comes to just trying to figure out how to use that in, well, for lack of better words, these general contexts,
Yeah.
it's just a little less intuitive. So it was like, kind of struck me that that's exponential and logarithmic and how that works here.
Exponential and log are inverses of each other. Remember, that's how this equation gets solved. When Abdul was explaining this, 2 to the L.
Well, right. I know they're inverse. I was just saying why that even begins to work here.
Yeah, that's a tough question to answer, perhaps. I'm going to get rid of the sort of like nitty-gritty details and just kind of like, right, this is the gist of it right here. I mean, to me, this is very mathematical, right? Like, this is just like we're doubling a number. We're starting with 1 and doubling it. So we've got exponential growth. The question is, when does that get bigger than n? That's the trigger that causes the while loop to end. And so, the number of times you double is described by this exponential function. We want to know when that reaches n and gets bigger than n, actually. But then the moment that it reaches n is going to tell us how many times you run through the loop. And so, yeah, you solve that. And it's very mathematical. It's just you solve it for n. We solve it for L and get log. So, yeah, let's maybe move on from this one. That might have to sit with you for a little bit. Think about that. I've heard, like, in my reading online about this subject, I have noticed that, like, log time complexity seems to be the hardest one for people to grasp.
Yeah, it's not intuitive, honestly.
Right. If it's
At
like
least to me.
linear, fine. If it's n squared, like twice through a for, or like a nested for loop, n squared, fine. But like this log one, yeah, I don't know. It's good. Let's move on to other stuff. So we haven't done, so there's a request to do something from 4.1, which I think would be great. We also haven't really done any actual writing of algorithms, which maybe we should do one of each of those. I'm going to start with Abdullahi's question from 4.1. We're going to go look at 4.1, number 17F. Yeah. Yeah, okay, 17F in 4.1 is we're supposing that A and B are integers. A is congruent to 4 mod 13, and B is congruent to 9 mod 13. I'm going to find C between 0 and 12 inclusive, such that F in particular, C is congruent to A cubed minus B cubed mod 13. Okay, so first of all, let's review what this mod business is all about. This congruence mod 13. When we say A, when we say here A is congruent to 4 mod 13 and B is congruent to 9 mod 13, this means that A is like some multiple of 13 plus 4. And B is going to be some other multiple, let's close this K1. B is going to be some potentially other multiple of 13 plus 9. And so this is for some integers K1 and K2, possibly equal to 0. So like A could be 4, or A could be like 17, which is 13 plus 4, or A could be 30, which is 2 times 13, 26 plus 4, right? A could be 3 times 13, 39 plus 4, which is 43 or whatever. So A could be 43. Yeah, it's always some multiple of 13 plus 4. You could take a negative multiple of 13 plus 4. So like negative 13 plus 4 is negative 9. A could be negative 9. It's one of those numbers. That's all we know about it. And B, likewise, a multiple of 13 plus 9. So now what we want to do is think, what's going to happen when you do A cubed minus B cubed? Well, it turns out that, and you can kind of read right at the end of section 4.1, it's talking about like all the properties that the integers modulo n have, or m, it uses m. And what it says is it's closed. One of the things that we know is that it's closed. Integers modulo m are going to be closed under addition and multiplication. So, and then there's like this consistency that you get with addition and multiplication. And so if we actually just take an example of a number, let me think about this for just a second. What I wanted to say was, if we take an example of a value that A could have, the simplest being 4, right? A could just be 4, and B could just be 9. If we take one of those and just do like 4 cubed minus 9 cubed, and then just figure out what that is, and then reduce it mod 13, like figure out what the remainder is mod 13, that should be the correct remainder that you get when you take any other A and B values, A cubed minus B cubed, and reduce that mod 13. So so let's see what the answer is going to be here. This is going to be I can't do arithmetic in my head like this here. Someone want to tell me what 4 cubed minus 9 cubed equals?
17. Negative 17.
Is that okay? So that's after reducing. This should be this is actually equal to like negative 665, right? That's the first thing, 4 cubed minus 9 cubed. But then we need to reduce that modulo 13. Where'd your negative 17 come from?
Oh, sorry, I did 9 squared.
Oh, yeah. That's okay. We don't want that. Yeah, I see what you're doing. Yeah. Okay, so we actually want negative 665. Thank you, calculator. And then we've got to reduce that mod 13. So to do that, we might have to do a little bit of guessing and checking on the calculator, because we are going to have to find a multiple of 13, which is like close to negative 665. What is the largest multiple of 16? No, the largest multiple of 13, which is less than negative 665. So what I'm going to do here, I'll show you my calculation that I'm going to do on let's go to Desmos. What I would do is like negative 665 divided by 13 is 51, negative 51 point something. So I think if we do 13 times negative 52, like rounding that down, that's negative 676. And then we do 676 minus 665 is 11. So I think what that means is negative 667 plus 11 is the negative 676. I'm sorry. Plus 11 is negative 665. There we go. So yeah, so it's going to be 11, right? It's going to be negative 665 is 11 more than a multiple of 13. 676 is our closest multiple of 13, which is less than it. And I got that just by doing this division and then rounding that integer down. Does that make sense?
Yeah.
So there's a yeah. I guess Abdul, you're the one who asked this question. So this ends up being equal to 11. Yeah, when you reduce it, this mod operation means basically divide by 13 and take the remainder. That's what it is. So it's basically, although it's because the remainder's always got to be a positive number. So yeah, that's what it is. So yeah, and then this like surprising result that we're taking advantage of here is just that you could have taken any number that's congruent to 4 mod 13 for your A, and any number that's congruent to 9 mod 13 for your B, and performed that operation. And when you reduce it mod 13, you're always going to get 11. So that is the sort of nice property of congruence that makes like Z, when you do Z mod M, or Z mod 13 in this case, it has all these nice algebra properties that things, algebra just works out and it gives you consistent results.
Quick question. So the 4 and 9 came from imagining that K and K2 were 0, right?
Correct. Yeah.
Okay.
Yeah. Which I just felt like was the easiest choice of numbers to work with.
So what's the difference between congruence and equality again?
So congruence means that they are in the same class, but they're not the same number. So like, for example, A doesn't necessarily equal 4 and 9, and B doesn't necessarily equal 9. We could have had A equal 17, right? And that's still congruent to 4 mod 13, because when you do 17 minus 4, you get 13, right, which is a multiple of 13. So like these two numbers are a multiple of 13 different from one another. In other words, 13 divides their difference, which is actually the way it's defined in the book. It's equivalent definition. So that's the difference between congruence and addition, like, sorry, and equality. Equality is like on the number line, you know, 4 is 4. The only thing that's equal to 4 is 4. But congruence is like you take that number line and you wrap it in a circle. It goes on forever. And then 4 is also congruent to 17, which is also congruent to 30, which is also congruent to 43, and so on. You know, so everything that lines up when you wrap it around, and how tightly you wrap that, like if it's a string, it's kind of like wrapping it around. How tightly you wrap that string is like what you mod it by. You mod by 13 is you're wrapping it around so that 0 matches up with 13, and then that's kind of the sort of circumference of your circle. And then what are the numbers that are going to line up with each other? Those are the congruence classes, and so all those numbers are congruent to each other.
And that's only for mod 13, right? And then you were getting those numbers from k equals 1, 2, 3, and 4. Or just plugging it in. Okay.
So just basically take 14 and take 4 and then add 13 to it any number of times, or subtract 13 any number of times. And yes, this is all mod 13. If we were talking about mod 10, then your circle, you know, your wrapped up number line would have like a smaller circumference, because you'd be going from, you'd be wrapping it so that 0 and 10 line up with each other, right? Then you go the numbers 0 through 9, and then you start over. So it's just like looping it around. They're taking the whole number line and looping it around, and then looking what things match up. So like 13, if you're doing mod 10, you'd have like 3 and 13 and 23 and 33 and 43, which would all be congruent to each other. Nice. 10 is easy, right? Because it's with our base 10 system, paying attention to congruence modulo 10 is super easy, because it just lines up with our like positional number system. It's anything that ends in 3. Yeah. So that was a good review of some stuff from 4.1. Glad you asked that. We're out of time, so we didn't get to everything. I know we didn't write an algorithm together here, but I do have office hours directly following this. So if anybody wants to stick around for that, we can maybe go over an algorithm, like writing an algorithm from scratch instead of just analyzing one. I know some people were asking about that earlier. I'm going to go ahead and end the recording now, everybody, okay?